Okay, good morning, everyone. Thank you for coming to the CRM-SSC Prize invited address. As you know, this year's award winner is Professor Linglong Kong. So Professor Linglong Kong is a professor in the Department of Mathematics and Statistical Science at the University of Alberta. He is currently the Canada Research Chair in Statistical Learning and the Canada CFAR AI Chair as well. He is a fellow of ASA and the Alberta Machine Intelligence Institute with over 120 publications in top journals. He and also published a lot of conference proceedings in the top conference, such as NeurIPS, etc. Professor Kong's research is widely recognized. He served as the associate editor for JASA, Annals of Statistics, Canadian Journal of Statistics, and Statistics and Interface. Additionally, he was a member of the executive committee of winner, chair of ASA Statistical Computing Session Program, and chair of ASA Webinar Committee. So his prior role include serving as a guest editor for CGS and Statistical and its Interface, associate editor for International Journals of Image Systems and Technology, guest associate editor for Frontier in Neuroscience, chair for ASA Statistical Image Session, and a member of the board of directors for SSC. Dr. Kong's research interest is widely ranged, including high-dimensional and neuroimage data analysis, statistical machine learning, robot statistics, quantum regression, trustworthy machine learning, and artificial intelligence for smart health. So today, he will talk about statistical aspects of trustworthy machine learning. Linglong, please start. You ready? Okay. Thank you.
Thank you, Jigo, for the introduction. And I first want to thank this SSC community. And the first SSC meeting I attended was 2007 when I was still a PhD student. It's almost like 18 years ago. It was the memorial. Second, I want to thank the award committee, Jigo Chad, and for choosing me. And third, I want to thank my mentor at U of A, Doug Wins, who's sitting here. And also, I want to thank my family, the support, especially Bai. She's not here. Okay, so today I'm going to share some of my research on the statistical aspects of trustworthy machine learning. It's mainly the work of my lab, J&K Statistical Learning Lab. And I also want to mention the support from Amy and one of the three AI Institute. So first, I will share some of the motivation why I want to do this research in trustworthy machine learning, and why our statistician can play a significant role in this area. And then I will share three projects we recently finished, and one is statistical inference for smooth quantile regression with streaming data, and the second one is Gaussian differential privacy on a remaining manifold, and the third one is distributional reinforcement learning with regularized Wasserstein loss. And then I have some closing remarks. Now, first, let's have a look at what's this trustworthy machine learning. This is a concept being popularized in the last 10 years. And it's mainly referring to the models that they are robust, have some private, have some fairness, and also could be interpretable. And all these sort of key features, if you look at that, for example, the first one, robust. That's what we have been, our statisticians have been doing for like for more than several decades. Like last week, I was attending this international conference on robust statistics in Italy, and this conference had been going for more than decades already. And also, I recall when I was doing my PhD, one of the conditions I passed my candidate exam from Doug Wins is I have to read these two textbooks. One is from Peter Rossoff, who just gave a talk yesterday, and the other one is Hilbert's Robust Statistics book. And so when I first get to know this area, I feel like our statistician definitely can make a big contribution on this area. And of course, there are some certain challenges. For example, with the technology, now the data are becoming more complex with or without structure. Also, this sort of high dimensionality and also some more changing data type, for example, streaming data. So how, as our statistician, how we study this kind of data to develop methodology and also to have certain guarantee, theoretical guarantee. And that's the challenge. Of course, like I said, our statistician will definitely can make some big contributions. For example, this quantity uncertainty. We do the inference, we do counting interval, we do hypothesis tests. We definitely can make contribution in this area. And also for this sort of privacy, and the privacy right now in US Bureau, we use differential privacy. But years ago, decades ago, we actually use statistical disclosure control. It's definitely part of statistics. And also, we can certainly guarantee certain distributional robustness. And one of my research area is quantile regression, right? And this certainly can provide certain robustness against sort of mean regression. And the last one is sort of interpretability. This is definitely of statistician. Almost the first day we learn statistics, we trying to interpret, for example, linear regression. We're trying to interpret the coefficient. What does that mean? And we all know, like, okay, we fix other covariates. If that certain covariance increase 1 unit, on average, how the mean will behave, right? So our statistician can certainly make some big contributions for this trustworthy machine learning. And the key message here is our statistician can provide theoretical guarantee to make all significant contribution to these four challenges, like uncertain quantification and privacy guarantee and robustness and its generalization. This model generalization is a very big thing in machine learning, right? And we use certain data and we build a model, okay? And then we want to see whether our model would be applicable in some other area. And then how we quantify the certain features of the original data. And in order to make sure the model we developed would be able to use in the new data. So nowadays, sort of transfer learning and domain adaptive, and all these things actually our statistics can make some significant contributions. Now let me first share the first paper, the project, which is about this smooth quantile regression, and it was recently accepted by Journal of Econometrics. And the first two authors were my postdoc. So this is a statistical inference for smooth quantile regression with the streaming data. If you look at the title, you will find there are three significant things. One is statistical inference. This is certain uncertainty quantification. Okay. The other one is sort of a quantile regression. This is certainly robustness. And the third one is a new feature, streaming data. streaming data only been popularized or been emerged in recent years, although in CS and engineering it's been there for quite some time. But for our statisticians, we only started to make big contributions in the streaming data recent years. Now, first, let's recall this sort of quantile regression and also our setup for the data. So we have DS, which is the S batch data set. Okay, so for this data, we have response Y, we have feature X, and this D means we have D1 to DB. So that means we have a totally capital, let's say capital B batch of data. And here we also denote a kernel function. We require it to be symmetric kernel. And for empirical quantile loss, we have this integration here. This F hat T beta is the empirical distribution. And this iota is this check loss function, and this I is indicator function. And from this, we can get the estimate of this toss quantile. Now, for quantile, one important feature or challenge is this sort of a check loss function. It's not smooth. Right? And we like things to be smooth, then we can easily implement a lot of theoretical things, and also in terms of algorithm, we can easily develop a lot of algorithms. So it's not smooth, then what do we do? And if it's not smooth, we can use some smooth function to approximate. It has been well developed in quantile regression community. And one of the early, also very popular version is sort of this kernel smoothing method. Okay, kernel smoothing method. We have this indicator function. Okay, it's not smooth, then we just use a kernel function to smooth it. And this kernel smoothing can satisfy most of this theoretical development and algorithm development. But for kernel smoothing, the smoothing is not enough in a sense. It only provides smooth first order information. Okay, only first derivative exists. And in streaming data, it's not enough. So there are some recently repopularized smoothing method. We call it convolution type smooth method. Okay? Instead of smoothing the indicator function of the quantile loss, we smooth the empirical distribution. Because we observe data, we have the empirical distribution, and the empirical distribution also get involved in this indicator function. So that's the sort of a convolution type smoothing method. What's the good thing about this convolution type smoothing method? It's twice continuous differentiable. So in a sense, we can find not only the first derivative, but also the second derivative. And this is very important when we deal with streaming data. Now, let me illustrate how this works in this streaming data. We first look at this sort of a low-dimensional situation. And for this low-dimensional situation, we have a B batch of data. We're trying to estimate these quantile coefficients. And now the quantile loss, the loss function is sort of smoothed version. We first consider a simple scenario. We have two batches. Let's say we have first batch, and we estimate the coefficient already. Now we get the second batch. So the key thing is how we are going to estimate or update our estimate when we get new batch of data, and what kind of information we need from the first batch. of course, well, the ideal situation, we can store all the data, but it's not practical, right? And for example, even nowadays in this top high-tech company, they won't be able to afford to store all the data. And usually they just sample like 20% or even less. So we will use these two-batch situation to look at what kind of information we should remember, we should store from the first batch. Okay. Now we get the estimate. This beta 1 had tilde, and we get the second batch. We want to get the estimate, updated estimate of this base star tilde 2, and hopefully we don't need any subject level data. That means we don't need to remember all the data from the first batch. Let's recall this beta 1 tilde, it actually satisfies this loss function, makes the loss function equal 0. And this equal 0 can hold exactly, not in the quantile situation. This may not be exact 0, close to 0, but may not be. And then this base star tilde 2 satisfies this condition, this just loss function equal 0. Then we find for the first batch part, it can actually approximate by this one. Therefore, recall this small quantile loss is continuous. It's twice continuous differentiable. Therefore, we can do this sort of Taylor expansion, and then we make sum of the term equals 0, so we can get rid of. So eventually, what we would have this beta 2 tilde certify this is the minimizer of this one. Okay. Now, if you look at this one, okay, you will find this actually coming from two parts. This part is the second batch, is the data. We get the full data. We have subject level data. Well, the first part, you will see from the first batch, you have the estimate, okay, and also you have a sort of second order information, okay, second order information. So what does that mean? If we put this all together, we will see, and if we previous have B-1 batch, and now we have the batch B coming, and we have this part is coming using the full data of the batch B, and this part from the previous B-1 batch. We only need to remember the previous estimate and also some summary statistic, of course, the second order information from all the previous batch. Okay, so therefore we don't need to store all the data, and we can still get get our good estimate. So that's the whole streaming data update. So what we need is we have the current data batch and DB, and then we need to store some summary statistics from the previous batch. Then we can we call it renewable update. Now this is low dimensional situation. What about a high dimensional situation? For high dimensional situation, usually we have this sort of a sparsity assumption, and let's say the dimension size is P, and we have S0 important features. So our goal here is we want to get the estimate. That's one thing. The second thing is, as I said here, we want to do sort of a statistical inference. Okay. Why I want to emphasize this sort of statistical inference. There are 2 points. One is, remember, for the trustworthy machine learning, we want to quantify the uncertainty. So that's also one thing our statisticians are good at. We can do the inference, right? That's actually one thing we make us different from the CS people. So we want to do this inference. On the other hand, as a statistician, we all know, if we want to do inference, our estimate would be, we have more restricted requirement on our estimate. Because we know for the estimate, we usually have, consistency. And then the next level is we have some asymptotic distribution, then we can do inference. So, and here, it's the same. That's why I emphasize this sort of statistical inference. Now, let's first look at how we get the estimate. And we want to get sparse estimate. We all know then to get a sparse estimate, one way to do it is we add a penalty. Let's say we add this L1 penalty. And as previous, the first term, this first term can be expanded into this 2 terms. One is current batch data, one is summary statistics. But now we get some other challenges. What's the challenge? That's tuning parameter, it's lambda b. In offline situation, we can access all the data. To estimate this tuning parameter, we can just use cross-validation, right? But now we have streaming data, okay? The data coming in batch. And for the previous data, we can only access the summary statistics. So how do we choose this tuning parameter, this regularization parameter, lambda b? That's a challenge. Here we propose a rolling original recalibration method. We adopt this method. So the key message is, the key thing is we regard the previous cumulative data set as a training set. Okay, we get the estimate. And then we use the current data batch as a test data. So when the current data batch arrives, we select lambda b through this criteria. Okay, but why we call it a rolling original recalibration? It's because here, even though this time we choose this lambda b, from a lambda candidate set, we still need to calculate all the rest. Okay, we choose this lambda b, but for the rest of lambda, we also need to calculate the estimate. And then we can rolling. Afterwards, we can do the estimate. Why? Because in this step, as you can see, you need to remember this, right? So for each candidate lambda, you still need to remember. You still do the estimation. That's the only thing here. Now, that's how we get the estimate. But like I said before, also I emphasize we need to do statistical inference. Only get the estimate is not good enough. Especially we all know for this Lasso estimate, it's not root inconsistent, right? And therefore, it doesn't have a tractable limiting distribution. And we cannot just use it to do the inference. So what do? We actually can introduce a sort of debugging process. In order to do this debugging process, we first need to get a good estimate of this sort of second order information, this Q to the B. It contains this Jacobi matrix information, and we need to get a good estimate. In order to do that, we need to solve this optimization problem. Basically, we need to get the inverse of this part. And after we get this theta, this big theta, then we can have our DBAS, online smooth DBAS quantile regression estimator. This estimator, which is defined as this one, beta B DBAS, is the original estimate without the debassing, the previous version, plus two items. First, you can see if B equals 1, that means it's an offline situation. We don't have this sort of streaming data. It will reduce to the offline situation. Then we have two additional terms. Okay, one is a debassing term. We want to get rid of bias. The second term is error correction. The debassing term is coming from this online generalization of this offline debassing term. That's an offline debassing term, and which is generalized to online version. The error correction term is coming from, remember, for the information matrix, we need to solve our optimization and to approximate. So we introduce additional error. Therefore, we have this sort of error correction term. Okay. If we look at this DBAS estimate closely, we will find eventually we need those information. We need those summary information, H1B and H2B and Q2B. These three items are needed coming from these two terms. In addition to that, we need the current date batch. So that's our estimate of the whole methodology. Okay, and one is if we don't need to do a variable selection, we only need to remember one second order information and the current batch data, and also the previous estimate. If it's high dimensional situation, we need to do debassing in order to get a good estimate, and we need remember, of course, some additional information like in here, we need add some more information, and then current batch data, we can get a DBAS estimate. Now, as a statistician, once we develop our methodology, we want to see, what kind of guarantee we want to have, right? What kind of guarantee we want to have. We have the following theoretical property. We'll just briefly introduce those. The first one, in low dimensional situation, we have the consistency asymptotic normality, which means, okay, even though it's streaming data, we use some summary statistic from previous batch and the current batch data, we update our estimate. We still can get close to the offline situation, For the high dimensional situation, it's a little bit more involved. We first need to study this property of this sort of consistency, and we characterize it in two ways. One is we look at R1 loss, one is we look at this R2 loss. Okay, and this is without debiasing. It's consistent, but it's not good enough, as I said. So we need to do debiasing. In order to do debiasing, we first need to verify the property of our information matrix. How good is estimate of the information matrix? So this is some theoretical property of our information matrix. Then on the top of that, we would have the asymptotic sort of distribution property of our DBAS estimate. Okay? And our DBAS estimate will follow the ZG plus WG. This is the the limiting distribution, and that is this sort of Bahadur format, this linear format. And put all this together, we can find the asymptotic variance of this part. Therefore, we can do inference. We can do inference. Okay. Then I will just show one simple simulation. And here we have this low-dimensional case. We look at the homoscedastic model and also this heteroscedastic situation. We have this fixed batch size, 100, and the total sample size. And we look at different criteria, like the average absolute bias, this average estimated standard error, and this empirical standard error, this coverage property, and average confidence length, and so on. And we look at this tau equal 0.5 and tau equal 0.2, and also 0.8. We compare it with this sort of offline situation, because the challenge here is the data is coming in a streaming format, right? We find it's actually quite close to the offline situation, and especially when tau equals 0.5, well, tau equals 0.2 and 0.8 is not as good as tau equals 0.5, which is understandable because at the center part, more information available. So the methodology perform better. And also we have this bike sharing demanding data, and we have some potential factors. For example, our temperature, humidity, wind spread, and so on. Our result confirm of our intuition. Not only that, we are able to give this quantitative quantify of the how this, for example, this wind spread affect this bike sharing demand. Okay, so this is the first project I want to share. Now, let's look at this second project. The second project is Gaussian differential privacy on remaining manifold. And this was published in NIPS 2023. And the first author, Yangdi Jiang, going to graduate on the job market this year. And Xiaotian is our postdoc. Yi is at York University. Lei going to go to University of Manitoba. Now, what's differential privacy? For a differential private algorithm, it achieves privacy by ensuring any individual record will not have a huge impact on its output. Okay? With you or without your data on the data set, the result won't change much. Then people won't be identify you. Okay? People won't be able to identify you. And so for epsilon delta privacy, there are two parameters. One is epsilon, one is delta. And the smaller the epsilon, the more privacy we are able to provide. And our goal usually is we want to achieve sort of a better data utility while safeguarding the data privacy. Because basically, for data privacy, you need stirb the data. Okay, stirb data. And in many ways, for example, you can add noise, right? And then once you stirb the data won't be the same as original data, right? But you want the data to be as close as original data, right? So this is sort of data utility. You want to keep the data utility, okay? Now, in our statistical analysis, we know a lot of times we may have data not coming from Euclidean space, okay? or we have some sort of nonlinear data. For example, we have remaining manifold data. For example, we have a covariance matrix, right? It's actually located in a manifold. And in this case, we want to have better data utility. And for example, we want to release a sort of M-value statistical summary. Meanwhile, we also want to have certain data privacy. For example, we want to have certain privacy guarantee from this Gaussian differential privacy perspective. Now, let's first recall what's if-and-dirt DP. If-and-dirt DP. So basically, we have data releasing mechanisms. We say it's if-and-dirt DP, and if the data only change by one record, so we have data D and D prime. Okay, the difference between D and D prime is only one record. In this case, the data releasing mechanisms will satisfy this condition. Okay, satisfy this condition. Now let's first look at assume this delta equals 0. We do some linear algebra. Then we will see this actually just mean the log of the ratio of the probability will less than or equal to epsilon. So that means the probability won't change that much. And so this is the epsilon-dirt differential privacy. How do we achieve this epsilon DP? And usually we need this sort of sensitivity of the data. And we can add some noise. For example, we can add this Laplace noise. Of course, we can also add a Gaussian noise. As most of our statisticians prefer this Gaussian noise. Okay, and but like we previously said, what this is usually for the Euclidean data. Okay, the data is a linear data. What if the data is located in a non-Euclidean space, for example, in manifold space? There are some works to do that. For example, we can have this remaining Laplace mechanism, okay, remaining Laplace mechanism to achieve this epsilon DP. And we can also have this sort of a Gaussian mechanism. Gaussian mechanism, that means when we add noise, we add Gaussian noise to achieve this epsilon-dirt DP for symmetric positive definite matrix with log Euclidean matrix. And this is very special manifold. Now, what's the motivation for our work? And epsilon-dirt DP is quite early. It's almost 20 years. And the first paper on epsilon-dirt DP is 2006. But as we do more and more study in differential privacy, we actually realize the epsilon-dirt DP may not be the best way to achieve differential privacy. There's some other mechanism. For example, recently we have this Gaussian differential privacy. Okay, for this Gaussian differential privacy, it got a lot of good properties. But how we extend this Gaussian differential privacy into the manifold situation, we don't have any work. So that's our motivation. We want to extend this Gaussian differential privacy to general remaining manifold. And how do we do that? We trying to develop sort of the remaining Gaussian mechanism. Okay, let's first recall what's Gaussian differential privacy. Gaussian differential privacy actually is a type of FDP. It's kind of variation of the that can generalize the vanilla Epsilon dp from this hypothesis testing perspective. And this Gaussian differential privacy actually is a 2022 GISP discussion paper. I was thinking why I started to do research on differential privacy in 2017, but it took me a couple years to really understand it. Until this Gaussian differential privacy, I feel I really understand what's going on, because this Gaussian differential privacy is based on hypothesis tests. For example, this mu differential privacy, mu GDP, that's actually how we distinguish two normal distribution. One is standard normal. One is a normal distribution with standard deviation 1 and location mu. So it's coming from this hypothesis test. That's another reason I like this GDP a lot. Okay. Now, how do we generalize this GDP in this manifold situation? It's not that easy. To achieve GDP, of course, we can add this Gaussian noise. We also have some property on this, let's say, mu GDP. We know that mu GDP, privacy mechanism is mu GDP if and only if it's epsilon dot mu epsilon dp. Why we want to use this connection? Like I said, this epsilon dot dp actually can easily generate to the manifold situation, but the GDP is not easy. For one thing, if we want to generate GDP, generalized GDP in the manifold situation, we have first to generalize this Gaussian noise in the manifold situation. Okay. Now, like I said, this hypothesis test-based GDP is hard to work on manifold. Epsilon dp is well defined on manifold, and also we have this sort of a connection between this mu GDP and epsilon dp. So we want to use this connection to develop our methodology. Now, one challenge is this Gaussian noise. In manifold, how the Gaussian noise looks like. And here is one way to generalize Gaussian distribution in the manifold. We have this remaining Gaussian distribution. It has the following distribution format. If you look at this one, you will see it mimics some of this Gaussian distribution in Euclidean space. Right? First, we have this sort of quadratic form, right? And we also have this sort of normalization parameter part that is sigma. Okay, this eta, as in this Euclidean situation, is a location parameter, and in manifold we call it footprint parameter. Okay, this sigma in Euclidean situation we call it variance, and here we call it read parameter. And it seems okay. Here we have this remaining Gaussian distribution, right? If we want to certify the Gaussian GDP in manifold situation, we just add some Gaussian noise. But we actually have some issues. And here is the big issue. One is, okay, we have to require this constant, normalization constant that it sigma to be finite, okay. But it's not all the manifold would certify this one, even though it may not be a big issue. For example, for our statistician, most of the time the manifold, we use this Harman manifold. We can restrict it to this manifold with lower bounded sectional curvature. Then in that case, okay, this Z sigma will be finite. This issue is not a big problem, but this Z sigma depends on the location parameter. Eta. Okay, if we recall for the Euclidean situation, the normalization parameter doesn't depend on the location, right? Doesn't depend on the location. But here it does depend on the location. And then you may ask why it's a problem, because later on when we compute the density ratio, then it's going to be a problem. Remember, this GDP is hypothesis test based, right? We need to compare these two density, two probability density. Okay, now in order to achieve this Gaussian differential privacy in the manifold, and we can first, okay, assume the manifold have lower bounded ridge curvature. And then if we have this global sensitivity parameter delta, then the remaining Gaussian distribution with this footage FD and ratio sigma will satisfy this mu GDP. It seems the problem is solved. But in differential privacy in GDP, you know it satisfies this mu GDP, but you want to find what's this mu. You kind of say, okay, it's satisfied. It get a constant. Then what's the constant? Here's the same. You say, okay, it satisfies this mu GDP. What's this mu exactly? Because we know, for example, we distinguish two normal distribution, a standard normal and another normal distribution with mean mu variance 1. Then what's this mu will make a big difference. If mu is 10, then it's very easy to distinguish them. If mu is 0.0001, then it's very hard to distinguish them, right? And here is the same. We know it's mu GDP, but what's this mu? We need to find this mu. Okay? And we indeed have some theorem about this mu. This mu, if we have the remaining Gaussian distribution with footage FD and the rate sigma, we know it's mu GDP. If and only if mu satisfies this condition. Okay, satisfies this condition. Well, that's good. We know if mu satisfies this condition, it will be mu GDP. That means we hope we can get this mu from those conditions. But unfortunately, it's very challenging to do this. It's very challenging to do this. And in practice, it's very hard to achieve this, to characterize a relationship between rate sigma and privacy budget mu. Okay. Now, fortunately, we look at some simple situation. For example, in this S1 manifold, we can easily find those kind of relationship. We can easily find mu. Okay. Actually, when we first submitted this paper, and we stopped here, but the reviewer said that's not good enough because S1 is too easy. S1 is too easy. Okay. I'm not going to go through the algorithm. And then we have a closer look at this inequality 7. And we find the important thing we want to evaluate is these two integration. Okay, to evaluate the integration, we know we can use MC, right? We can use MC to evaluate those integration numerically. But we still have a challenge. We have this super. Okay, this super. This causes problem. And this part is related to this normalization parameter is related to the location. Okay. Now, here is these two challenges. One is the density ratio. Okay. One is this super. Okay. We attack these two problems one by one. We first start with this set A, and we want to look at how this set A looks like. We look at this RD situation. Okay. And we find in this RD situation, this set will become to this one, and then 7 reduced to this situation. And this is the same as the Euclidean Gaussian mechanism. This gives some our hint. We actually under this constant curvature assumption, the super over the neighborhood data set can be removed. So we don't need to do the super if we have a constant curvature. Therefore, we can use this MC to approximate the integration. So that's the first, the super, we can remove it. And then we have this algorithm. I'm not going to go through this algorithm. And then we have some simulation study, and we look at two situations. The first one is our situation. The second one is a sort of a naive implementation. We convert a mu GDP to the equivalent epsilon DP, and then generate the privatized mean using sampling. Then we use this remaining Laplace distribution mechanism. Then we compare these two methods. And here is the result. And the red one is our method, and the blue one is the Laplace mechanisms. As we can see, our Gaussian mechanisms always achieve better utility. Especially with a small budget. If the budget is small in this area, we are way better than Laplace. Well, if the budget is large, for example, mu is 4, and then the gain in utility is less. And one of the reasons is there are much fewer perturbations with large mu for both approaches. So the difference would be subtle. Another reason is the algorithm tend to overestimate mu with this small sigma. And I also want to point out, if mu is large, then the privacy protection is actually kind of small. You think about if you want to distinguish standard normal distribution with a normal distribution, get a mean 4 varies 1, then it's kind of easier. Well, the important part is when the mu is small, how we going to distinguish them. Okay, so this is the second project I want to share. It's about differential privacy, and the third project I want to share is a little bit away from our statistics community, and I call it statistics in reinforced learning. And I started to reinforced learning when I get my tenure. I feel a little bit safer to explore very different area. But I know I'm a statistician, and I should explore some area would be related to my research. So I have certain advantage in that area. So the area I start to look at is this distributional reinforced learning. I will briefly introduce this project. You will see why I want to explore this area. So the project I want to share with you is this distributional reinforced learning with regularized versus stand loss. And the first author is Sun, and he's now a postdoc with Susan Murphy at Harvard University. And this paper was published in New Reps 2024. And I also want to say I get into reinforced learning largely by the encouragement from Rich Sutton. And Rich, some of you may know, just get this Turing Award in March. And he lives in the same neighborhood as me. And he usually likes to do jogging around in the neighborhood. And a lot of time, especially in summer or spring, when he passing through my house, sometime I'm outside, he would stop by, talk, and always trying to encourage me, said, Linglong, you're a mathematician, you should do something about this reinforcement learning. And that's how I start. And this picture is the first AI week held by Amy. It's right after, it's 2022, right after COVID. And so Rich likes dancing, and he said, Linglong, you should work out your comfort zone, come dancing with me. And I just tried a little bit, and my student took a picture. Okay, I don't want to talk too much about this project. I just give some introduction. And for reinforced learning, the key thing is we look at this cumulative reward. We want to maximize this cumulative reward. But in classical reinforced learning, we have this sort of value function. Okay, as you can see, here the reward RT is a random variable. So the cumulative reward, even with this discount factor, is still a random variable. Okay, in classical reinforced learning, we actually look at the value function, which is Q function. Okay, this Q function is same as the Q learning. And what's this Q function? We take the expectation. So for classical reinforced learning, we're trying to find the optimal policy. Trying to maximize this value function. Trying to find a good strategy to maximize this value function. Well, for distributional reinforced learning, we are not just learn the mean. We're trying to learn the whole distribution. Okay, we learn the distribution of this cumulative reward. Okay. If we put this it in this way, okay, this is what classical reinforced learning do. We look at this value function, which is mean. This is the distributional reinforced learning. We learn the whole distribution. Okay, we learn the whole distribution. Okay, now why I said this area is the area on reinforced learning I first get into. You think about, okay, what's the alternative of mean? It's quantile, right? If we learn enough quantile, we basically will learn the return distribution. I've been doing quantile regression for like more than decades. I thought, maybe I will be able to, catch up and from this part. It turned out, yes, indeed, I actually was able to catch up, made some contribution in this area. Okay, and for the distributional reinforced learning, there are two key challenges. Okay, in classical reinforced learning, we have this Bellman equation, Bellman operator. Okay, a lot of algorithms is based on this Bellman operator. Why? Because for the Bellman operator, it's a contractive operator. Therefore, we can use fixed point iteration. Okay, a fixed point iteration to find that fixed point, and it's guaranteed to be the optimal policy we are looking at. We just do it iteratively, because it's a contractive map. Well, for distributional reinforced learning, we are not just learn the mean, we learn the whole distribution. The same as second project in the manifold, right? And in the Euclidean space, we can use, usually we use L2. Let's say we use Euclidean distance. But what about in the distribution function space? What kind of distance we should use? And how we choose this statistical distance between two distributions will affect whether this distributional Bellman operator is contractive or not. Okay, that's one thing. The second thing is, okay, I think most of our statisticians know when we deal with distribution, okay, it's a little bit challenging in a sense. Here, we don't know what kind of distribution, okay. In our traditional statistics study, we have normal distribution, right? In that case, we already parameterize it. For normal distribution, it can be characterized by mean and variance, right? And then we have gamma distribution. We have what format. We have some parameter. But in this reinforced learning, we want to learn this distribution. Now, we have no format and what kind of distribution we have. How do we characterize, how we parameterize this distribution? It turns out there are some simple ways. I said one already. Let's do a couple quantile. Then we can characterize. That's one way. This is actually one method in distributional reinforcement learning. We call it QRDQN, quantile regression deep Q network. And another one is C51. C51 is a very interesting name. Why it's called C51? C, that means categorical. 51, that means the method choose 51 support point. You choose 51 support point, and for each support point, you have a probability mass. So basically, you characterize that distribution. You can characterize that distribution. Okay, this is two main challenges. Okay, two main challenges. There are many methods in distribution reinforcement learning already, and in our work, we actually introduced a new algorithm based on sinkhole divergence. So this sinkhole divergence defined as this one. It gets two parts. One part is coming from this optimal transport, and another part is coming from this KL divergence. That's why we call it, because this epsilon part, we call it regularized Wasserstein distance. And by introduce this distribution, this distance, we are able to guarantee the contraction property of the Bellman operator. And also for the distribution, to characterize distribution, like I said, we can use support point. We can use quantile. That's also another very naive way to characterize the distribution, which we use all the time. It's just sample. We have some sample points, then we use just pure empirical distribution to approximate that distribution. That's what we use in this project. And I'm not going to go to all the detail. And we actually showed our method by choosing this tuning parameter epsilon, it can get connected. For example, if epsilon tends to 0, it goes to this Wasserstein distance. If epsilon go to infinity, it goes to this MMD distance. Well, our method can also choose epsilon between 0 and infinity. And I will just show some some simulation. Okay, in reinforced learning, the simulation usually when we develop methodology, okay, we try it in this Atari game. Atari game is kind of, for example, the Super Mario is one of the Atari game, and it's developed like in 1970s, 80s. We have this small machine that we can use it. Yeah, and we test our methodology in this 50 Atari game, and we have this algorithm. One is DQN. DQN is traditional reinforced learning framework, and actually DQN was published in 2005 and in Nature, and this DQN is base of this AlphaGo, AlphaFold, all these algorithm. And the C51, as I said, they choose a 51 supporting point. QRDQN, they choose different quantile, and the MMD is one other alternative method. This SYNC is our method. And this is some selected game, okay, some select game in Atari game, okay, and we look at this mean of human normalized score, the median and interquantile mean. Okay, as you can see, the red one is our method, and in general, all the distributional methods, C51, QRDQ, MMD, and SYNC, they are better than the black one, which is the classical reinforced learning method. And overall, our method, which is the red one, can perform better than this all other methods. But this is selected. We select those. This is also one of the criticized in computer science. You only show the result. It's good for your own method. We are actually not. We also show all the other method. Here is this our method, SYNC, distributional reinforced learning versus QRDQN, and this part is we perform better. This part, this blue part is QRDQN perform better, and as you can see, most overall we perform better than QRDQN. We are not saying for every game we are better than QRDQN, and here is we compare with this MMD DQN. It's the same. Overall, we perform better. Okay. Then the closing remark. And for one thing, as I showed in this 3 project, and our statisticians can make significant contribution in this trustworthy machine learning from this robustity perspective, from the differential privacy, which is quite related to robust statistics, and from this distributional reinforced learning perspective, we all can make contributions. And also we can recall this 4 challenge, 4 perspective, and rethink about how our statistician can make contributions. For example, this interpretability, and one very important tool the recent year is this influence function. But you think about influence function is purely, I actually learned a lot when Doug forced me to read these 2 books about this influence function. Yeah, and I also want to share some of work in our lab we are doing, and trying to see what we can contribute. And for example, for the recently privacy preserving statistics for fair machine learning for online and continual learning, for reinforcement learning. Of course, we also do a lot of traditional statistics, for example, high-dimensional data, neural image data, functional data analysis, and so on. I think that's all. Thank you.
So we have set up the microphones here. So if you want to ask questions, can come to in front of the microphones. And because our talk is recorded, so please come to the microphones when you ask questions. Yes.
Hello, thank you very much. Could you please give an example of the type of data that would not use Euclidean distances, or a Riemannian manifold would be better, especially for the privacy concern?
Okay. For privacy concern, okay, we first start to provide privacy of some summary statistics. For example, mean. Okay, then what's next? Varies. Okay, then what about more than one dimension? We have covariance matrix. What's covariance matrix? It's positive definite matrix. And positive definite matrix is actually located in a manifold. And also in image data analysis, and we have some DTI, different tensor image. And the different tensor image is actually a 3x3 positive definite matrix. And that's, for covariance matrix at summary level. And for DTI data, it's at the subject level. We all need this kind of privacy. Yeah.
Any other questions? If you want to ask a question, please come to the front. Yes. So we can, if you have questions, you can also line up here, and so we can save some time. So yes. Okay, go ahead, Tianyu.
So thank you, Dr. Kong, for the nice presentation. I have a question about the streaming data. So when you present your method, is there any requirement about the streaming data, like what are the frequency of the streaming data, and what are the amount of data in each streaming data? Do they have an impact in the methodology?
Thanks, Tianyu. Good question. We indeed have to have a certain requirement on the batch size. Otherwise, let's put it this way. Otherwise, practically it works, but theoretically we just cannot provide the theoretical property. And because I present 3 projects here, so for the first project, we did have this sort of a sensitivity study on the batch size. And if the batch size doesn't satisfy this certain condition, this renewable process may not work, and it'll getting better, and then it get worse and worse. It may divert. Yeah.
So a follow-up question is that, like, for the batching data, do we need to assume that they follow the same distribution, or is it possible that there are some shift of distributions for the streaming data that we collected over the time?
For renewable process, yes, but that's also the 5th topic our group working on. It should be online and continual learning. And for continual learning, we actually don't require the distribution to follow the same distribution. And the distribution can have a shift. And for those kind of data, we can use continual learning technique, or we can use transfer learning technique. But one key thing is you have some idea how the data going to change, how the data going to be different.
Okay. Yeah.
It cannot just like the data is coming and I have no idea how it would be, and then, yeah.
Yeah. Thank you very much.
Thank you.
Any other questions? Please come to the front.
Thank you, Dr. Kong, for your presentation. I have a question about the last project. You mentioned about the choice of the divergence and the distance. Can you explain more about how this choice of the divergence or distance have an impact on the resulting algorithm?
Okay.
Yeah.
Maybe I will go back to. Okay. For example, and here we list 4 distributional reinforced learning method, and C51, QR, DQN, MMD, DQN, and Sinkhor distributional reinforced learning. Okay. For C51, we use 51 supporting point, and this is the first paper on distributional reinforced learning. So they actually use KL divergence to characterize the distance between 2 distributions, which is natural, right? Because we have supporting point. And that's a very interesting story in a sense. Later on, the community find KL divergence won't guarantee the convergence of this distributional Bellman operator. But for C51, or in computer science, when they do the algorithm, sometimes they tend to do projection. Okay, so even though they claim they do this KL divergence, but in algorithm they actually use projected KL divergence. Projected KL divergence actually is Kramer distance. Kramer distance actually can guarantee the convergence. So that's the first one, C51. They use projected KL divergence. It can guarantee the convergence. The QR, DQN, we use quantile to characterize the distribution. A natural way of the distance choice is Wasserstein distance, because Wasserstein distance is the inverse of the 2 distributions, the difference, and so on. And it turns out Wasserstein distance indeed can guarantee the convergence. And this MMD DQN, why is called MMD? Because they use MMD distance, and it also guarantees the convergence. Of course, our method, this Sinkhor, this regularized Wasserstein distance also can guarantee this divergence. I think there is one paper characterized in what kind of situation the distribution, the distance of the 2 distributions should satisfy in order to have the Bellman operator to be contractive map to guarantee the convergence. Yeah, that's one particular theoretical paper to talk about it. Yeah.
Just one quick follow-up. So does it matter that 2 distributions, they are absolutely continuous with each other? Like if for divergence, we need this to be absolutely continuous, but Wasserstein distance does not require. Does it matter in this kind of context of discussion? Just whether the distributions are absolutely continuous with each other, which means that they have kind of
I think
equivalent.
In this framework, whether it's absolutely continuous or not, it doesn't matter.
I see.
Because even you think about it, we use C51, we find the 51 support to represent the distribution, and it's very far away from absolute continuous already, right? Yeah.
Okay, thank you.
Thank you.
Okay. Thank you for all the questions. If you have more questions, you can talk with Linglong privately. So can you join me to thank Linglong again for his great talk? Thank you.